Okay, thank you very much. Welcome to EPA's monthly webinar series, Challenges and Treatment Solutions for Small Drinking Water and Wastewater Systems. This month's topic is the removal of multiple contaminants, biological treatment, and ion exchange. So there's some information on the screen, and this webinar will allow you to ask questions. So you can type your question in the text box that's located in the lower section of your screen. And please feel free to do that while the speaker is presenting so that we can organize the questions so that when both speakers are done, we can ask both speakers the questions for them. If you're interested, we do have a certificate for continuing education contact hours, or 1 hour for this webinar. You need to be registered to get that CEU. A little bit of information on that is that the requirements: you must be registered, as I previously mentioned. You must attend for 60 minutes. If you are in a room with others, the names of the people who are not logged in must be provided by the person who is. And please send the names to the address listed there. Unfortunately, we cannot give out certificates of completion for reviewing this presentation on the ASWA site, because this presentation will be located there after today, but we cannot give CEUs for watching that webinar recording, only for this live webinar. Okay, so just one more comment, if you missed the poll and there's more than one person in your room, please go to the question box and tell us how many people, if there are more than one person in your room. That helps us catalog how valuable this webinar series is. So I will go right into presenting our first speaker, Trevor Boyer. Dr. Boyer is an associate professor at Arizona State University, where his research interest is water sustainability, with many research projects on innovative applications of ion exchange technology. Dr. Boyer is a recipient of a National Science Foundation Career Award, and his research has been sponsored by the EPA and other federal agencies, including the Water Innovation Network for Sustainable Small Systems Center. Dr. Boyer earned his PhD and MS from the University of North Carolina and his BS from the University of Florida. And with that, I will hand it off to Dr. Boyer.
Okay, great. Thank you. Thank you for the introduction, and I appreciate the opportunity to be here today and share our work on combined ion exchange for removal of dissolved organic carbon and hardness. It's important that I acknowledge the funding agencies and others who have contributed to this work. This work has been supported by EPA STAR grants, Sustainable or Small, Safe, Sustainable Public Water Systems through Innovative Ion Exchange. I'm also part of the EPA Center WINS, Water Innovation Network for Sustainable Small Systems. I've had many great students at the University of Florida who've contributed to this work. I also have a great collaborator at the University of South Florida, Dr. Jane Jung. And we've worked in particular with the small system in Florida, the Cedar Key Water and Sewer District, and I've had some support from Tonka Water for the piloting parts of this work. So this is a recent article in Journal AWWA that probably many on the webinar are familiar with, that outlines the violations and deficiencies of small systems. And people on the webinar are probably familiar with different aspects and challenges of small systems as shown here. What I'm going to be thinking about today are sort of the treatment and the operation at a small water plant. And so here's a small water plant that I've worked with over the years in Florida. Their water source is a shallow groundwater, and it's high levels of dissolved organic carbon, high hardness, variable amounts of iron. And so they start with oxidation at the wellhead. That's followed by the MIAX process, magnetic ion exchange, which is an anion exchange process used to remove DOC, dissolved organic carbon, followed by lime softening, sand filtration, and chlorine disinfection. And so in visiting this plant and talking to the operators, the lime softening requires a lot of effort on their part. And so in looking at this plan, I always wondered, well, why couldn't we just use the ion exchange vessel and remove the dissolved organic carbon and hardness there in a single vessel? And so it's a relatively simple idea that's shown here, where let's take a single vessel and call it combined ion exchange, eliminate the lime softening process. We're going to have to add now both anion exchange resin and cation exchange resin in that vessel, and that's going to allow us to remove both the DOC and hardness. So again, a relatively simple idea, but it's an idea that we've gotten a lot of miles out of, because we think it has a lot of potential for small systems, because you're taking sort of one simple process and you're using it to remove multiple contaminants. So to provide now a little background on ion exchange, in case it's a process of water treatment that you're not familiar with, to help for the later results. What we have here on the left side of the screen is thinking about ion exchange at the molecular or micro scale. And so shown here is an anion exchange resin. That's a polymer bead that's positively charged. So associated with those positively charges is a negative counterion. In most cases that would be chloride. And then that chloride exchanges with your contaminant anion in solution, which could be dissolved organic carbon, could be nitrate, could be other anionic contaminants. And then on the right side of the screen at the macro scale, that's the scale that we observe. At the simplest level, we could think of ion exchange as a sort of black box process where we have the contaminated water in and the contaminant-free water out. And of course, we don't want to treat it as a black box, but just for illustration here at this point, we see the micro scale and macro scale of ion exchange. Taking that same approach for regeneration, at some point the ion exchange resin becomes exhausted with the contaminant. So that's shown here, where the resin's exhausted with this contaminant X minus. And so then to desorb that contaminant, the resin's going to be subjected to a high concentration solution of sodium chloride, where the chloride will displace the contaminant. And so we see that over on the right, sodium chloride into our ion exchange process, and then sodium chloride and contaminants out. So those are the two basic pieces of ion exchange that we need to understand, both the treatment side and the regeneration side. And so then that allows us to think about combined ion exchange. And so here now what we would have is, in a vessel, we would have both anion exchange resin to remove negatively charged contaminants and cation exchange resin, often used in the sodium form, to remove positively charged contaminants. And for us, the contaminants of interest are dissolved organic carbon, which in water, most dissolved organic carbon behaves as an anion, and that the other contaminant we're interested in is hardness, in most cases calcium hardness. So dissolved organic carbon, most are aware, is a concern because it's a disinfection byproduct precursor, and it also exerts a chemical demand through the other stages of water treatment. So there's many compelling reasons to remove DOC and get high levels of DOC removal. Hardness and calcium hardness isn't a health concern, but it is a sort of an economic concern and an aesthetic concern during water treatment. And there's many water plants who remove hardness, and so we saw this as an opportunity for again, this single process to remove multiple contaminants. I wanted to make sure I made the point here early on that although I'll be showing my results are mostly, the results we have are mostly focused on dissolved organic carbon and hardness as a set of multiple contaminants, really this idea can be extended to a wide range of multiple contaminants. Maybe it's nitrate and hardness, maybe it's DOC and other metal cations. By no means this work is limited to DOC and hardness, and what we've tried to do in the work I'll present is really get a strong or a deep understanding of both the science and the engineering of this process, so that we can take what we've learned for dissolved organic carbon and hardness and apply it to other multiple contaminants of interest. One other piece of background information is the reactor configuration. On the left we have the fixed bed reactor that most are probably familiar with ion exchange or other filtration or adsorption processes, and then a completely mixed reactor with resin recycle, as shown here, where the advantage of this completely mixed process is that the ion exchange process can happen earlier in the treatment train because turbidity and head loss isn't an issue. And so we study both of these processes for ion exchange, and I'll be sort of going back and forth between fixed bed, and completely mixed in terms of where our results apply. So I want to start with some proof of concept work where we had this idea of, why don't we just take this anion exchange process and think about it in terms of a combined ion exchange process. And so in that experimental design, the basis of it was doing a series of jar tests. So we received groundwater from Cedar Key, moderate level of DOC here, around 5 milligrams per liter, hardness approaching 300 milligrams per liter. And we worked with 2 magnetic ion exchange resins. And so for those of you not familiar with these resins, these are polymer resins that have magnetic iron oxide incorporated into them, and that allows for more effective settling and allows those resins to be used in a completely mixed process. And then we wanted to look at different modes of jar tests where we're looking at simultaneous treatment, the resins combined in the same vessel, and sequential treatment. That is either anion exchange followed by cation exchange or vice versa, to understand the chemistry and the process together, and then looked at regeneration. And so this is one of our first results of the combined ion exchange, and for a lot of the figures here, I'll give the take-home message below, often there in a yellow box. And so in this figure, to orient you, we have the cation exchange process that's signified by the MiX sodium, the anion exchange process by the MiX chloride, and then using the resins together in the same vessel. And we're looking at hardness, DOC, and UV absorbance in terms of percent removal. And so the take-home here is that we were able to achieve on the order of 70% DOC removal, 55% hardness removal in this single process. And in fact, if we take those jar test experiments and we look at the overall water composition as shown here with pH, dissolved organic carbon, hardness, chloride, sulfate, and we compare it with the finished drinking water, we see a very a similar composition resulting from this single process, the combined ion exchange, versus the full treatment train, which is dominated by the anion exchange process and that separate lime softening process. So then we did some additional work looking at the sequence of treatment, and so here we have on both of these figures along the x-axis is the state of the resin, fresh resin, 1 time regenerated resin, 2 times regenerated resin, 3 times regenerated resin, looking at hardness removal on the left, DOC removal on the right, and then the different modes of treatment, either simultaneous, that is both resins together, or sequential. And if you do the statistics on all of this data, what you see is there's really no difference between doing the simultaneous treatment or the sequential treatment. We did see some interesting trends in terms of, with sort of increasing regeneration cycles, a decrease in hardness removal, and a trend of an increase in DOC removal. We think that was due to sort of fouling and buildup of calcium carbonate or calcium on the resin. But overall, this beginning work gave us some of the insights we needed to further develop this process. And so just some quick conclusions here to move on. We saw that we could use the anion exchange resin and cation exchange resin in a single vessel to simultaneously remove DOC and hardness, and then we could effectively regenerate those combined resins in the same vessel. We looked at the order of treatment, and we saw that sequential and simultaneous showed similar results. And here, we also looked at some of the regeneration in terms of, using tap water. Is there any concerns here with the tap water in terms of hardness and alkalinity when we're trying to do this combined ion exchange process? Some observations moving forward. One observation was that the cation exchange resin, I didn't emphasize it earlier, but you might have noticed in the figure, the cation exchange resin removes some DOC. And that's not something we would expect. The cation exchange resin is designed to remove things like hardness. So why was it removing DOC? That was an interesting science question for us to pursue. And then we also thought that there could be some other interesting applications of combined ion exchange, such as thinking about it as a pre-treatment of membranes, because you're going to be able to, again with this single process, reduce both organic fouling and inorganic scaling of the membranes. So then we felt at this point we needed to focus more, or we needed to study deeper the cation exchange piece of combined ion exchange. And so we did that by working with, again, with the Cedar Key groundwater and also making some synthetic waters to mimic the Cedar Key groundwater. In this case, we looked at both this magnetic ion exchange resin, which is a little more of a, kind of a research product, and then looked at a sort of standard off-the-shelf cation exchange resin that a plant might use now for softening. And then we did some interesting thing in these experiments in terms of using the resin as you typically would, which is in the sodium form. Sodium's the exchangeable cation. But then we also put other cations on the resin, shown here, calcium, magnesium, strontium, barium, to try and understand how would this resin behave as it started to accumulate these other cations, and how would DOC possibly interact with these cation exchange resins. And so all of those results are summarized here. And let me just get you oriented. On the left we have the magnetic resins, and what's signified there is what form is the resin in. Is it saturated with sodium, calcium, magnesium, etc.? And then on the right is the polymer, just your conventional polymer resin with the same resin forms. And then we're looking at DOC removal, but the way it's plotted here is C over C0, so that C over C0 of 1 means no removal, and a C over C0 of 0 would mean complete removal. And then we also looked at a variety of waters, looked at a calcium-only hardness water, a magnesium hardness water, a mixture, no hardness. So there's a lot of information here, but the two take-homes were that we consistently saw DOC removal by this magnetic cation exchange resin for the variety of resins and waters, and no DOC removal by the non-magnetic cation exchange resin. And so what that was able to show us was that it's actually this iron oxide component of the magnetic ion exchange resin that's actually acting as a absorption site for the DOC. So that leads to its own sort of interesting sort of research that I'm not going to sort of elaborate on further today, but this idea of having this very sort of bifunctional sorbent where it could function as both a cation exchanger and really an anion exchanger or a sorbent. But moving forward, we're going to work with the polymer cation exchange resin so that we have, since that's doing solely the cation exchange, and also because the magnetic cation exchange resin had a very low capacity, and we need a higher capacity resin for this process due to the amount of hardness that's often present. So one other piece that Katie did as part of this cation exchange work was to again look at this simple question, but something that's useful as we move forward, especially in terms of process modeling, and that is now that we've sort of understand the differences between the magnetic cation exchange resin and the traditional polymer cation exchange resin, can we really just simply view combined ion exchange as an additive process? And so the way that she looked at that was in terms of looking at different constituents here, bicarbonate, calcium, magnesium, and sulfate removal, looking at different water types as shown on the x-axis, calcium waters, magnesium waters in terms of their hardness, and then different resins. So just doing an anion exchange experiment, just a cation exchange experiment, combined ion exchange, and then adding the individual data. And so the take-home when we look here and we compare, for example, the colors here are a little tricky, but that darker gray bar to the sort of shaded bar, for most of these constituents, they're a similar height, telling us that the combined ion exchange, when we have the same resin, both resins in the same vessel, versus summing up the individual reactions, we get the same removal. So some conclusions here, just to summarize what I've shown, was that that DOC removal from the magnetic cation exchange resin is coming because of the unique properties of that magnetic resin, and that we didn't see any DOC removal for the polymer resin, and then that the cation exchange, or excuse me, the combined ion exchange process is additive. So now we felt like we were at the point where we understood some of the basic science of this combined ion exchange process, and we wanted to think about it in a more realistic way. And so what we did was we collected some different groundwaters in Florida that are characterized by high DOC, high hardness. So that is, candidate waters for this process. We continue to use the magnetic anion exchange resin because from previous work we've done, that's a very effective resin for DOC removal, although there are other sort of non-magnetic resins out there that are useful and can remove DOC well. And then we went with a sort of off-the-shelf standard cation exchange resin, and we did that again because we were looking for a higher capacity resin for the hardness removal. And so then what we did here with our jar test was we did sort of a tweak to the jar test procedure. And this jar test procedure here is called multiple loading jar test, and it's designed to try and mimic more of a completely mixed process, or sort of a fluidized bed, where you're thinking now in terms of bed volumes processed. And so we set up this with the resin ratio, so with the amount of anion exchange resin present and the amount of cation exchange resin present. We had a 4-to-1 ratio, meaning, and so that results in these different bed volumes. So conceptually it might be a little hard to visualize, but you're processing the same amount of water, but because you have different amounts of anion exchange resin and cation exchange resin, that's why we represent it here by the 1,000 bed volumes of anion exchange and the 250 bed volumes of cation exchange. And then we looked at regeneration with sodium chloride, kind of a low-level spectrum here, or 2% on one side and all the way up to 20% on the other. So here are the results, a lot of results here, so let me walk you through them. Along the upper subplots are all DOC concentration, and the lower subplots here are all hardness concentration. The x-axis in all of these is the bed volumes treated, and so the data symbols correspond to each sort of increment of bed volumes treated. And then for all of this data, we looked at both fresh resin and regenerated resin using this sort of lower strength 2% sodium chloride solution. And then we also did some work at the higher 20% sodium chloride solution, trying to kind of span a range of regeneration conditions. And so if you look through these data, for example, if you look through the upper subplots at the DOC removal, you see that you can see along the y-axis the initial DOC concentration, and then you see we get DOC removal in most cases down on the order of 1 to 2 milligrams per liter, and it increases with subsequent bed volumes. But what we want to think about really for this process is that composite sample that corresponds to the sort of overall water produced over the course of those 1,000 bed volumes. And if you were to look at the composite sample for those three upper figures, the DOC removal is in the range of around 70 to 85%. Then if we look at the bottom figures here, we get something that kind of resembles the sort of breakthrough behavior we would expect to see for a cation exchange resin removing calcium. And but again, what we're visualizing, or what the sort of produced water, the water that's produced, would really be this composite that would be produced over the course of these 250 bed volumes of treatment. And if we look there at that composite sample, the hardness removal is around 50%. And we think that's kind of the target where we want to be, right? We want to maximize DOC removal because we need to then in turn minimize the formation of disinfection byproducts. But we don't need to necessarily maximize hardness removal, right? We're not trying to achieve 100% hardness removal. We're trying to get something on the order of a 50% reduction in hardness removal. So we thought that these batch conditions, or these laboratory experiments, were getting us closer to understanding how this process could really operate at a water plant. So a little side thing that we did was thinking about applying this to nanofiltration concentrate. And so we collected NF concentrate from 2 membrane plants in Florida. And these membrane plants were selected because they were treating groundwaters with high DOC and high hardness, and so that resulting membrane concentrate then was further concentrated in DOC and hardness, as shown here, on the order of say 30 to 50 milligrams per liter DOC, 1,000 milligrams per liter of hardness. So we took the same resins, the magnetic anion exchange resin, the polymer cation exchange resin, followed that same multiple loading jar test procedure, looked at sodium chloride regeneration. And so similar figures, but I switched the order a little bit, where the two figures, the two plots on the left are the DOC concentration, in the middle here is sulfate, and then on the right is hardness, all in terms of absolute concentrations. And again, if we look at the composite samples that would be produced by this process, these composite samples are producing water that shows 70 to 80% reduction in DOC, around a 50% reduction in sulfate, and a 90% removal of hardness. And so if we were to think about how this could fit in at these existing membrane plants, we have the feed water to the membrane, then we have the concentrate that's produced. We could pass that through the combined ion exchange process. The treated concentrate then would approximately resemble that initial feed water, so then that could go through an additional secondary membrane process. And so this was something that we had worked on a while ago, and it's still kind of out there in terms of some niche applications for combined ion exchange. So conclusions here is that through these laboratory experiments, we're starting to now take our science, our sort of scientific understanding of the combined ion exchange and operate it in such a way that we think is meaningful for a water plant. And then when we're looking at these composite samples produced by the combined ion exchange process, we're seeing greater than 70% removal of DOC, 50% or more removal of hardness. I should also mention, I could talk about this separately, but these bed volumes of water treated are sort of reasonable amounts of water that are being put through the process. And then we can also, in the second bullet here, think about applying combined ion exchange to concentrate streams, whether it's NF concentrate or maybe there's some interesting wastewater or industrial applications for this combined ion exchange as well. So now spend a few minutes talking about where we currently are with combined ion exchange. And currently we're doing several different pilot plant studies of combined ion exchange. And so these are the two current students, Jareen and Elise, working out at Cedar Key on some of the ion exchange pilot plant work. And so as I said, we're at Cedar Key, we're at this small drinking water plant. Right now, the DOC is on the order of about 5 milligrams per liter. It does vary somewhat because of it being a shallow groundwater. And then the hardness is approximately 300 milligrams per liter. We're using two just polymer resins. We're using a polymer anion exchange resin and a polymer cation exchange resin. And just some of the highlights of the pilot plant operation. Right now, the results I'm going to show are for fixed bed. I'll make some comments towards the end about the work we're doing on a completely mixed process. But right now, the results are fixed bed in downflow columns. The resin, and so in these columns, we have both anion exchange resin and cation exchange resin. And right now, we're working at this sort of 1-to-1 resin ratio, and so that each column contains 4 liters of anion exchange resin and 4 liters of cation exchange resin. Each column is operating at a target of 0.5 gallons per minute. And we're doing quite a bit of work on the regeneration side as well. One of the things we're looking at is, and it's kind of it's related to some of the other research we're doing and some of the other projects we're involved with, is looking at alternative regeneration agents to sodium chloride. And so in this case, we're looking at potassium chloride versus sodium chloride, and we're looking at both of these at a 12% solution. So I underline the resin ratio and regeneration because those are really the two key things, in my opinion, to sort of understanding and making this combined ion exchange a viable process for small water systems. The resin ratio is interesting, and we have lots of other data we can show and talk about at some other time. The resin ratio is really interesting because you need to get this balance in terms of, on the service side, getting to your target levels of removal for your contaminants. But then you also have to balance the resin ratio during the regeneration side, and you need to have the right proportions of resin and regeneration chemicals so you can effectively regenerate the resin. And this kind of goes back to an earlier comment I made about thinking about other contaminants. For us, we're focused on this DOC hardness system, really trying to understand the science and now understand the sort of process operation. And it's these insights from the resin ratio and regeneration that's going to allow us to take this combined ion exchange process and apply it to other multi-contaminant situations as well. So here's some results from looking at that 1-to-1 resin ratio of 4 liters of anion exchange resin, 4 liters of cation exchange resin in a downflow column. The figure on the left is hardness, and on the right we have DOC. We're showing the bed volumes of water treated on the x-axis, and both the hardness and DOC concentration are shown as C over C0, where C over C0 of 1, it means no removal, and a COC00 means complete removal. The way this experiment was designed was that it was operated over 3 regeneration cycles, each regeneration cycle lasting for 1,000 bed volumes. And so that's why you kind of see this break in the data at 1,000 bed volumes and 2,000 bed volumes. And I also changed the symbols to help you see, the circles correspond to the first cycle, the diamonds the second cycle, the squares the third cycle, and then the color coding, the maroon data, correspond to using sodium chloride for regeneration, and then we have a parallel column, all the same conditions except that the gold symbols correspond to using potassium chloride. And so if we look at these results, what we can see is that, if we take a look at the hardness data first, somewhere between 250, 500 bed volumes is when we get breakthrough of hardness, and then over the 500 to 1,000 bed volumes, we approach saturation of the column and we no longer achieve any hardness removal. And so that data is kind of consistently showing that over the 3 cycles. And when we look at the regeneration samples we collect and we try to do a mass balance on the sort of regeneration efficiency of the process, we're seeing that we are desorbing the majority of the calcium that goes onto the resin, and so we are getting effective regeneration, and that's shown here in these results where we get this sort of repeat performance for each cycle. If we look over at the DOC removal, what we see is this sort of this initial leakage of DOC, meaning that initially about 20% of the DOC is coming out of the column, giving us sort of an initial DOC removal of around 80%, and then over the course of the 1,000 bed volumes, the DOC removal deteriorates, and we're seeing about 60% DOC removal at 1,000 bed volumes. And again, when we look at regeneration, we are effectively regenerating the resin. We're desorbing the DOC, so that on cycle 2 and cycle 3, we're seeing on the average similar performance as an initial cycle. I wanted to show you the data here in terms of absolute concentrations. It's a little messier, so I wanted to show that sort of normalized data first. But what you can see here, so the way this data has been changed is it's just the y-axis is the absolute concentrations. Those x's are the raw water entering the columns, and so you can see the data for hardness and DOC. And then the plus symbols there are the water being produced, the finished water at the CRQ water plant. And so you can see how this process is performing with respect to both hardness removal from the pilot and the finished water, and DOC removal from the pilot and the finished water. So so on par with what this existing plant is doing. A lot more data that we could show here, and actually we'll be presenting some of these results at the American Water Works Water Quality Technology Conference in November. So if you're there, please stop by and see us. So let me just summarize now sort of where we are with this ongoing combined ion exchange pilot plant. Regeneration is a major emphasis of this, and as some of you might guess, when you regenerate the combined anion and cation exchange resin, you can have precipitation. We're looking at the effectiveness of alternative regenerants because we think there can be some disposal advantages. We're going to be looking at different column operation, and that is a way for us to maintain, say, a consistent 50% DOC removal, 50% hardness removal, 70 to 80% DOC removal. We think the lead lag column operation could allow us to do that. We're also in the process of piloting sort of a mini completely mixed combined ion exchange process that we'll be able to compare with the column results I showed. Just wanted to mention that as part of this piloting work, we're also comparing sodium chloride and sodium bicarbonate regeneration just for the anion exchange side. Collaboration with University of South Florida and the Wind Center, we're doing process modeling, life cycle assessment, decision support tool, really trying to bring together all the knowledge we have on combined ion exchange and putting it into sort of a usable format for small systems. And that's kind of what's shown here, where we're thinking about the upstream impacts in terms of where does our regeneration chemicals come from. Today's talk is focused a lot on the treatment and regeneration, but then we're also thinking about the disposal options as well. So with that, I'd like to thank you, and I'll be happy to answer your questions during the Q&A portion.
Okay. Thank you, Dr. Boyer. Thank you very much for that presentation. A couple of housekeeping notes is that first of all, that I forgot to mention at the beginning, but it's not too late. On your panel, you can see a section called Handouts, and that's the file of the slides. So if you want to look at the slides offline or on your own, you can. You can download those slides if you wish. Also, if you missed the survey and missed it initially, and there's more than one person in your room, please indicate that in the question box. We'd love to see how many people are listening in to the webinar. If there's only one person in the room, that's fine. You won't have to do that. But if there's more than one, we'd gratefully appreciate it. And with that, I'll introduce our second speaker. If we run a little past the hour, we'll still have questions afterwards for both speakers. Our second speaker is Nicholas Dugan. Nicholas Dugan is an engineer in the EPA's Water Supply and Water Resources Division. In his 19 years at the agency, he has performed or supervised bench and pilot scale studies to evaluate the removal of nitrate, nitrite, ammonia, perchlorate, and DBP precursors through biological treatment processes. He has a BS and an MS from the University of Cincinnati and a BA from Carleton College. He is a licensed PE in Ohio. And with that, I will pass it over to Nicholas Dugan.
All right, let's get this presentation up on the screen. And hold on, let me get the slideshow going. All right, there we go. So I'm going to be talking about the removal of multiple contaminants through biological treatment. And the way this presentation is going to be organized, we're going to start with a little bit of background about some of the contaminants that we'll be discussing today. Then we'll move through some science basics. Then we're going to present some bench scale treatment results from a combined anaerobic and aerobic biological treatment system. Then we'll move on to presenting the results of a pilot scale anaerobic study where nitrate and perchlorate were removed simultaneously. And we'll finish up with a pilot scale aerobic ammonia treatment study. So moving into the background, we'll start with ammonia. And ammonia is a contaminant that a couple of the ways that ammonia can get into the water supply is either through wastewater discharges or through remnants of fertilizer application. And this ammonia is not currently regulated by the Environmental Protection Agency, so there's no MCL for it out there. But it is because of the fact that it serves as the starting point for biological nitrification, so the conversion of ammonia to nitrate, that if it's a compound that if it propagates through the distribution system, it can support the establishment of nitrifying bacteria in the distribution system, which in turn can lead to a host of maintenance and operational issues. And this map that I'm showing you was generated in a study by the U.S. Geological Survey, and they're looking at ammonia concentrations in groundwater throughout the United States. And a perusal, the take-home message from this map is that ammonia shows up in wells across the country, and that there is a significant fraction of the wells where the ammonia concentrations are, high, over 1 milligram per liter. Moving on to nitrate. So nitrate shows up in the water a couple of different ways. One is just through the natural geochemical cycling of nitrate as part of the global nitrogen cycle, of nitrogen as part of the global nitrogen cycle. And another way is as the end product of the nitrification process, which is the biological conversion of ammonia to nitrate. And this map was generated once again by the U.S. Geological Survey, and they did a study of over 1,000 wells where they followed nitrate concentrations for 10 years. And the upshot from the study is that the statistically significant increases in nitrate concentration outnumber the statistically significant decreases in nitrate concentration in these wells, and that the nitrate is once again it's a widespread. It shows up in wells across the country. Looking at perchlorate, let's go back to nitrate. So nitrate is regulated by the Environmental Protection Agency at a maximum contaminant level of 10 milligrams per liter as nitrogen in the finished drinking water. So moving on to perchlorate. Perchlorate is a compound that is it's part of solid fuel oxidizers that are used in the production of military ordnance, and these oxidizers also show up in civilian applications in the production of pyrotechnics that include things like flares and fireworks. And perchlorate is regulated at several different concentrations at the state level, and for example, I think 2 micrograms per liter in Massachusetts and 6 micrograms per liter in California. And this table is a summary of perchlorate detections in selected states. It was generated once again by the U.S. Geological Survey. And the take-home from this table is that perchlorate shows up not necessarily frequently, except in the case of Nebraska, but consistently, in states distributed across most of the breadth of the country. So with a little bit of background under our belt, we'll move into some science basics for biological treatment. And for the purposes of this presentation, we're going to define biological treatment as any process that uses seeded or indigenous bacteria to remove an undesired substance, either from finished drinking water or from drinking water treatment residuals. And for the remainder of this presentation, we're going to be focusing on the removal from on the production of finished drinking water. So then seeded bacteria, for the purposes of this presentation, we're defining seeded bacteria as bacteria that are isolated from the environment because they exhibit the ability to remove or participate in the removal of a contaminant of interest. And then these bacteria that enriched in pure culture and then seeded into either enriched in some way, for example, in pure culture, and then seeded into a biological contactor where they then hopefully establish a population that will remove the contaminant of interest. What are indigenous bacteria? We're defining indigenous bacteria as bacteria that are naturally present in the source water, and they're being allowed to colonize the biological contactor without any additional enrichment, and are capable of removing the substance of interest when the proper conditions for their growth and maintenance have been provided. So in a biological contactor, where does the bacteria live? They will attach to any solid surface, and these include solid surfaces of media that are typically used in drinking water treatment. So for example, filter sand, anthracite, granular activated carbon, and synthetic engineered media, which include things like pulse saddles, burl saddles, and rascia grains. Bacteria can also be suspended in the water column in a suspended growth process. And going back to the attached growth processes, when they're attached to media hydraulically, these units are operated typically in one of two ways. They're either operated in a downflow mode, so hydraulically very similar to a typical rapid media drinking water filter, or they can be operated, these units can be operated in the upflow mode as a fluidized bed process. For the remainder of this presentation, we are going to look at biological contactors that are operated in the downflow configuration. There's a range of substances that can be removed through the biological drinking water treatment process, and these include organic ozonation byproducts. And the benefit of removing these is that they lower the probability of bacterial regrowth in a distribution system. Also, biological processes can remove natural organic matter, which will in turn lower the probability of the formation of disinfection byproducts. Then on the inorganic side, ammonia and perchlorate, nitrate, and bromate, the latter of which is an inorganic ozonation byproduct, are all substances, inorganic substances that lend themselves to removal in biological treatment processes. And one of the big advantages of biological treatment processes is that there tend to be, if it works out right, it eliminates the need to treat a residual waste stream. So moving into how a little bit deeper into how the process works, there's two major divisions of biological treatment processes. So on one side, you have processes that operate in the presence of dissolved oxygen, and they're called aerobic treatment processes. And then you have processes that operate in the absence of dissolved oxygen, and they're classified as anaerobic treatment processes. Looking at aerobic respiration, organic carbon will serve as the electron donor and as the carbon source, and then dissolved oxygen will serve as an electron acceptor. And bacteria are going to derive energy and synthesize biomass from the organic carbon. And the byproducts from this process include carbon dioxide and water. And these are the processes. This type of process is what's used, for example, to remove natural organic matter or ozonation byproducts. Anaerobic respiration, once again, you'll have some type of organic carbon as serving as an electron donor and a carbon source. And then you can have oxidized inorganic compounds such as nitrate or perchlorate or bromate, which serve as an electron acceptor. Once again, bacteria derive energy and synthesize biomass from the organic carbon, and byproducts include carbon dioxide and water. And then the removal of, if the reduction process of the nitrate, the perchlorate, or the bromate go to completion, you end up, for nitrate, you end up with molecular nitrogen as the end product. For perchlorate, you end up with chloride as the end product. And for bromate, I don't have it here, but you end up with bromide as the end product of the reaction. Then a special subset of aerobic treatment is the oxidation of ammonia, and that's known as nitrification. And we'll have ammonia, in this case, serving as the electron donor. And then we'll have inorganic carbon, such as dissolved carbon dioxide or dissolved bicarbonate, serving as a carbon source. And bacteria will derive energy from the ammonia, and they'll synthesize biomass from the inorganic carbon. And we'll have oxygen serving as the electron acceptor. And the end products of this metabolic process include water and nitrate. So moving on into some treatment results, we have, we'll start out with a bench scale study where we combined anaerobic and aerobic biological treatment. And what we had is we had 3 contactors in series, and we first had a solid media downflow anaerobic contactor, followed by a reaeration column where water moved down and air moved up, and then we had a solid media attached solid media aerobic contactor, and the support media in all these contactors was sand. And let's see, we added for the anaerobic contactor, we added acetate as an extra electron donor and carbon source. And the main water through this was a bench scale study in the lab, so we used dechlorinated tap water. And the seed material was Rauhauer River water that we added at a very low concentration. That provided a constant source of indigenous microorganisms to supply bacteria that colonize the contactors. And then we added ammonia and perchlorate and bromate. So nitrate was naturally present in the water. And then we also added ammonia and perchlorate and bromate, to the mix. Here's a picture of the bench scale system, and I put this in here just to give folks a quick feeling for the scale of the operation. And then we'll move into our first data slide. And here we're looking at bench scale ammonia removal. And this study went on for, this particular phase of the study went on for about 150 days. And we'll start with total removals, which is indicated by the yellow symbols. And the removal data are normalized. And so basically they're presented along the y-axis, and we're expressing removal results as a fraction of the system influent that was removed at a given stage in the treatment process. And so the total removal symbols, and this are the yellow symbols, what these indicate is that after an initial acclimation period during the first 35 days or so, we observe complete removal of the ammonia through the biological treatment process. And then moving into drilling down into different unit operations, we'll start with the anaerobic treatment process, which is in green. And we observed small removals of ammonia in the anaerobic treatment process. And what we attribute this to is that that this was driven by dissolved oxygen that was still present in the very upper levels of the anaerobic contactor. Then during the first half of the study, we see that in the aeration column, which is blue symbols, and the aerobic contactor, which is the red symbols, we can see variable but roughly equal amounts of the influent ammonia were removed in both the aeration column and in the aerobic downflow aerobic contactor, which at the end of the process. And then during the second half of the study, what we observed is that almost all of the ammonia removal occurred in the occurred in the aeration column, and we had lower amounts of ammonia being removed in the aerobic contactor. And we attributed this to the, given the fact that our pH was between 7 and 8, which is a couple of order of magnitudes too low to support any type of effective air stripping, we attributed the results in the aeration column to the establishment of a culture of suspended microorganisms in the column, which were very effectively removing dissolved ammonia. Hold on, my screen looks like it's locked. And we're trying to move on to the next data slide. Let's see here. There we go. Okay. My apologies. Looking at this slide, we're looking at the removal of oxidized inorganic contaminants, and this happens anaerobically, and it's happening just in the anaerobic contactor. So this anaerobic contactor operated with acetate as the electron donor, and we added acetate through the study to hit a target concentration of 2 milligrams per liter as carbon. And once again, we're looking at the normalized removal along the y-axis. So the removal has been normalized to be expressed as a fraction of the influent concentration removed. And we'll start with nitrate, which is expressed as the green symbols. And what this indicates, normalized removals of essentially 1 indicate that we observed across the duration of the study complete removals of nitrate. And then for the bromate, which is the blue symbols, we observed during the first about 2/3 of the study, we observed highly variable removals of bromate until by about the last third of the study, we also observed complete bromate removals. Then for perchlorate, which is the red symbols, we observed during the first 2/3 of the study relatively low and variable removals of perchlorate. And then by the end of the study, we saw perchlorate removals climb till by the end of the study we observed complete reduction of perchlorate in the anaerobic contactor. And let's try to go to the next slide. Just bear with me, please. It looks like I apologize. It looks like I'm locking up.
Hey, Nick, this is Tom. You might, this happened to me also. If you click your mouse, perhaps that might advance the screen.
There we go. Sorry. Okay, I will do that. My apologies. Here we go. So now let's look at the concentrations of acetate electron donor at various points of the biological treatment process. And the reason this is important is because acetate is a compound that's microbiologically, it's incredibly labile. So it can be used by a very wide range of microorganisms, and and they have the capacity to gear up very, very, very quickly to consume any acetate that's in their environment. And it's something which can lead to very heavy accumulations of biomass in areas where you really don't want it if it's allowed to propagate through into the finished water. And so one of the things we track pretty closely is what happens to acetate in our pilot systems when we're adding it. And so we have influent acetate concentrations with the green symbols. And so we've got our average of 2 milligrams per liter of carbon in the influent to the anaerobic contactor. And we can see that for about the first half of the study, the acetate was completely consumed inside the anaerobic contactor. And then we see, we're still not sure what happened, but this is something that's one of the issues with biological treatment is sometimes you're not completely sure what's going on inside your contactors. But that being said, we saw acetate breaking through into the effluent of the anaerobic contactor, and that's the blue symbols. And then we can see that some of the acetate was consumed in the aeration column, so we have lower concentrations here in red for the aeration column effluent. And we saw that our aerobic unit contactor at the end of the study, any leftover acetate was always completely consumed in the aerobic biological contactor, and so we never saw acetate breaking through into the finished water of the of this biological treatment, of the overall biological treatment system. And what this points to is the need for, anytime you have a biological process in place, it is important to have some sequence of cleanup steps downstream before you transmit the finished water into your distribution system. Moving on to pilot scale anaerobic treatment results. This is a pilot scale anaerobic treatment system that we had installed at a local water treatment plant. And the goal of the study was to look at the impact of temperature variations on the anaerobic treatment process. And here's our anaerobic contactor. It's the large white unit in the foreground, and it just gives you some idea of the scale of the process. And the first data slide, we're looking at the anaerobic removal perchlorate as a function of temperature. And so we have this project was run for about 2 years, just under 2 years, and we have perchlorate concentrations are the dark symbols, about 50 micrograms per liter against the left-hand y-axis. Then we have that's influent perchlorate concentration. Then we have effluent perchlorate concentrations, that's the white symbols against the also against the left-hand y-axis. Then we have temperature in degrees Celsius along the right-hand y-axis. And what you can see is that after the initial 85-day acclimation period, we saw, for the most part, complete removals of perchlorate until the water temperature dropped below 10 degrees Celsius. And then as we moved into winter, by the depth of the winter, by which time we had we're observing water temperatures in the neighborhood of less than 2 degrees C, we observed no more, we observed zero perchlorate removal. And as water temperatures increased, in the spring, we observed, by the time temperatures got up to about 10 degrees C, we observed once again complete removals of perchlorate. Moving on to nitrate removal, once again, this graph is set up the same way as the previous graph. So influent nitrate concentrations are in black, effluent anaerobic contactor effluent nitrate concentrations are in white. Nitrate removal is established prior to perchlorate removal, and we can see essentially complete removals of nitrate until the water temperature dropped below 10 degrees C, and then nitrate removals were interrupted until the spring when water temperatures crossed the 10 degrees C threshold, at which point we saw, once again, establishment of nitrate removals. One of the things, if you have a contactor, if you have a biological contactor that's set up for nitrate reduction, one of the things you need to be careful of is that you're promoting the complete reduction of nitrate to molecular nitrogen, and that the process is not interrupted at some intermediate stage. One of the symptoms of the process of a biological nitrate removal process being interrupted at an intermediate stage is the appearance of nitrite in your contactor effluent. And so we saw nitrite concentrations. There was no nitrite coming into the contactor, very little nitrite to speak of. And then the contactor effluent nitrite concentrations in white against the left-hand y-axis. And we can see during the acclimation period, we saw some periods of high nitrate concentrations. And then also during the steady state operation period, we did see some nitrite appearing. And that includes during the period of low temperature period when we observed incomplete removal of nitrate. So just it's something that you need to be cognizant of if you decide to install a biological nitrate removal process. Moving on to dissolved oxygen. And the effluent contactor concentration of dissolved oxygen is another way that you can diagnose what's going on inside your anaerobic biological contactor. And we can see that during our acclimation period, effluent dissolved oxygen concentrations in white symbols dropped steadily until we, during the steady state period, where we consistently saw DO concentrations, dissolved oxygen concentrations, less than 0.1 milligrams per liter. And some of that, the concentrations may have been lower. It's just that the method we're using to analyze for dissolved oxygen, kind of bottoms out at about 0.1 milligram per liter. That being said, once temperatures dropped below the 10 degrees threshold, we saw very quickly a rapid increase in dissolved oxygen concentrations until temperatures dropped, once again rose above 10 degrees Celsius in the spring. Then we saw a resumption of low dissolved oxygen concentrations for the rest of the study. Another thing to be cognizant of in an anaerobic treatment process is what's going on with sulfate. So typically, what will happen is that compounds like nitrate and bromate perchlorate will be dissolved, will be reduced first, and then, but if too much electron donor is added, it is possible that sulfate will be reduced. And one of the symptoms of sulfate reduction is the appearance of hydrogen sulfide. And once we realized we had a hydrogen sulfide issue, we also started measuring for sulfide concentrations, and we can see that sulfide concentrations, during this study, we kept our acetate, our electron donor, our acetate electron donor concentrations constant. And so the only thing that was varying was the temperature, and we can see that effluent sulfide concentrations did track positively with temperature. Now, hydrogen sulfide production is something that in practice, in operational practice, is something that can be remedied very effectively by exercising control over your anaerobic, over your electron donor concentration.
Hey, Meg?
Yeah.
Nick, if you could wrap it up quickly, that would be great.
I will do that. Moving into the final set of data slides, we're looking at pilot-scale aerobic treatment results. And this took place at a groundwater plant in Ohio. And this was a system where the filters had already, where the filters were known to have established, support a community of nitrifiers, so bacteria that would remove ammonia. And moving into this data slide, we look at influent ammonia concentrations of 1.2 milligrams per liter with no detectable nitrite or nitrate. Then by the time we get to the filter effluent, we have all the ammonia has been removed and it's been converted to nitrate. And so the goal is pilot study. And the pilot study was used by tapping into the aeration contactor effluent, at which point there was still plenty of ammonia left. And here's a picture of the pilot treatment system to give you an idea of the scale of the process. And the goal here was to look at how quickly these units, filters could be started from scratch to remove ammonia using a number of different acclimation scenarios. So in acclimation scenario 1, we used virgin media. In scenario 2, so acclimation scenario 1, we used virgin media. In acclimation scenario 2, we used the top 3 inches of the pilot scale units were composed of anthracite from the full-scale filters, and in acclimation scenario 3, these units were seeded with a full-scale filter backwash water. And the data slide here, we're looking at effluent ammonia, the effluent concentration is a fraction of the influent concentration. And the take-home message from these slides is that even though the different acclimation scenarios resulted in different rates of acclimation, given sufficient time, by the time we get to the end of the study, all three of these pilot scale contactors were exhibiting a complete complete removal of ammonia. And then the mirror image of this is that this is conversion efficiency to nitrate. And so what we're seeing here is that by the end of the study, regardless of how these contactors were started, by the end of the study, we are seeing a complete conversion of ammonia to nitrate. So moving to conclusions, biological treatment has the potential to remove multiple dissolved inorganic contaminants, potentially in the same treatment system. One of the principal advantages of biological treatment is the minimization of treatment residuals. Ammonia removal by conversion to nitrate requires sufficient amounts of dissolved oxygen. Nitrate and perchlorate removal by conversion to molecular nitrogen and chloride, respectively, proceeds in the absence of dissolved oxygen, and care has to be taken to ensure proper dosing of the electron donor, proper acclimation of biological contactors, and some type of contingency or backup treatment during upsets or acclimation periods. And this concludes my presentation, and thank everybody for their attention, and I'll be open to any questions during the Q&A period.
Okay, thank you very much, Nick. We'll now get into the question period. So I think we have a little bit of time to go through some questions. Hopefully you can stay with us to hear the questions. With that, the first question will be for Dr. Boyer. So the question is that you showed a little bit of DOC removal with the cation exchange resin. Is there any DOC, what percentage of DOC has a positive rather than negative charge?
Yeah, that's an interesting question. I think from my experience, the fraction of DOC that would have a positive charge is very small, maybe on the order of 10%, but that's a number I could try and get a better answer for. I mean, from all the work we've done, the majority of DOC is negatively charged, and from the different experiments we did, we believe that it's the negatively charged DOC that was being removed by that cation exchange resin due to that iron oxide component.
Okay, great. Here's another question for you, Dr. Boyer. How long does it take to regenerate the combination of resin? Is it different than regenerating each one separately?
No, that's a great question. We looked at that in some of the earlier work, and we looked at separate and combined regeneration, and there's no change in the combined versus separate with respect to time. The cation exchange is a rapid process in terms of the regeneration. The anion exchange process can take a little longer because of the larger DOC molecules. So really it's thinking about the contaminants and the resin properties for the time to regeneration, and whether it's combined or single is really secondary to the contaminants and the resin properties.
Okay, great. And one more, Dr. Boyer. Would you see similar results if there were high levels of naturally occurring ammonia present? And would you expect ammonia removal too?
Okay, yeah. So what I would say is that kind of goes back to my comments about thinking about other multi-contaminant systems. And so if the ammonia, if the conditions were such that the total ammonia was present as the ammonium cation, cation exchange is an effective process for ammonium removal. So this could be operated, for example, as a DOC ammonium process instead of DOC hardness. So yes, if the ammonia was present as NH4+, then the combined ion exchange is a viable process.
Okay, great. Thank you very much. Here's a question for Nick Dugan. How do you control filamentous bacteria that can cause problems such as impeding flow?
When you're running a downflow biological treatment unit, one of the things you do is you actually keep an eye on your head loss just like you would in a regular rapid media filter. And so once your head loss goes above some predetermined level, you backwash, and you're actually looking for, in our experience with our pilot units, we're actually looking for the exact same things. You're keeping an eye out really for the exact same things that you're looking at when you backwash a rapid media filter that's designed for particulate control. So we're looking at clarity in the backwash water. We're also we're also keeping an eye out for formation of mud balls and any types of channeling. And in terms of what we found in our experience is that that typically, in terms of at a macro visual level, bacterial overgrowth tended to manifest itself more as biofilms and, in a colloquial term, to use a colloquial term, slime layers, slime. And so it was, it's the exact morphology of the bacteria, whether it was, whether it was, kind of spherical or filamentous didn't matter as much as, just the fact that they produced the kind of a macrobiofilm.
Okay, great. Thanks, Nick. Here's a question for you also. So you talked about ammonia and ammonium ions somewhat synonymously, and could you give a little background on that, please?
Well, I'll start off by apologizing, and that was simply the function that was a function of the fact that that I was not as careful as I should have been with what I put on the slides. So at the pH levels that we're operating at in our biological treatment studies, we were always dealing with the ammonium ion.
Okay, thanks for clearing that up. And then another one for you, Nick. So how applicable are these technologies with respect to small water systems and their resource challenged condition?
That's something that we're actively working on inside the agency right now. And I understand, especially when you're thinking about. So yeah, let's leave it at that. It's something we're actively working on. We're working very hard to simplify, the process. It depends on the treatment process too. For example, if your goal is to, for example, remove natural organic matter to minimize the probability of disinfection byproduct formation, that's something that, from an operational maintenance point of view, is much easier to pull off than anaerobic biological treatment in its current state. So it really depends on what you're looking at, and I think, though, that I'm optimistic that there's progress that's going to be made, on the simplification issue, over the next, half decade or so.
Okay, and this one's for Dr. Boyer, and I'm going to combine that one, I guess, with this one. So how applicable is the combined ion exchange for small systems, and what is the advantage from keeping it together as opposed to running separate vessels?
Okay, let me take a couple approaches to that question. So one would be, for a small system, what we see as the advantage would be replacing multiple unit processes. So for the water plant that I was referring to, they were using multiple unit processes to remove the multiple contaminants. So I think if you can downsize in terms of going from 2 or more processes to a single process, that's what we see as the advantage of combined ion exchange. And actually, why we're looking at the fixed bed as well as the completely mixed is to get a better feeling for which one is sort of more operationally sort of acceptable for small systems. So that's one answer. In terms of the advantages of the combined process to sort of the sequential process, I mean, that's a great one, and there's not a real short answer to that question. I mean, I think it would depend on other considerations, and actually that's what we're looking at now with the regeneration, is that it's possible that for some situations it does make more sense to separate the anion and cation exchange resin for that regeneration piece because of precipitation and scaling. And so that's something that we're looking into now. I would think, if we could have this single process that can remove multiple contaminants, we do the regeneration on this single process, footprint, operational simplicity, I think would all point towards doing it as a single process. But this pilot study is allowing us to look at that and to also, look then at having the processes separate as well. So I would say stay tuned. We're thinking about those questions as we're doing this work.
Okay, great. Thank you very much. And this one's for Nick. Could you talk a little bit more about system upsets and recovery times for biological treatment systems?
I think that it is, I think it's probably, I think a lot of this is it's site specific, so it's hard to generalize, but what I can, as an example, I'll talk about our bench scale treatment study where and this was on about a weekly basis where we were backwashing our anaerobic contactor, and the anaerobic contactor was backwashed with water that had a dissolved oxygen at saturation concentrations of about 8 milligrams per liter for the temperature we're running at. And what we found is that after a 10-minute backwash, and we backwashed for 10 minutes at about 50% bed expansion, and with sand media, and what we found was that after a 10-minute backwash, it took about 2 hours for dissolved oxygen concentrations to go from saturation to less than 0.1 milligram per liter, and then using nitrate as an indicator, I'd say it took after about 12 hours, we would find nitrate concentrations, nitrate removals back up to about 80% of what we'd observed before, prior to backwash, and then it took a full good 24 hours really for nitrate concentrations to get back to normal. And what this points to once again is that at this stage in the game, I think when you install a biological treatment process, there has to be there potentially needs to be some type of backup treatment downstream.
Okay, good. Thanks, Nick. This one's for Dr. Boyer. In your systems that you ran for the exchanged ion, such as sodium, what were the levels of sodium then in the effluent after treatment?
Yeah, that's a great question. I'd have to the question asker could email me and I could send some of the data. I don't have the number right now, but we are measuring that because in places like Florida, sodium has a primary MCL, and so that's one of the other kind of balancing acts to this process is making sure that as you remove hardness, for example, you don't exceed the sodium level. And so that's another reason why we've looked at some of the alternative salts like potassium chloride on the cation exchange side and sodium bicarbonate on the anion exchange side. With the potassium bicarbonate, or excuse me, with the potassium chloride, you're now using potassium as the counterion instead of sodium. And so we think that that has some benefits both for the treated water and for disposal. The challenge there is that potassium chloride is a bit more expensive than sodium chloride. So, do those benefits in terms of the treated water and disposal outweigh the bit higher cost of potassium chloride over sodium chloride?
Okay, great. Thank you very much. This one's for you, Nick. It's related a little bit to the previous question about upsets, but how do you reconcile biological treatment processes with the standards for drinking water?
It is this data. I think that if the biological treatment is, if a system is carefully engineered and conscientiously operated, that it is possible to I think it's possible to produce, to have a biological treatment system that in the end produces water that is, meets all the, meets all the guidelines. And we've generated a fair amount of data looking at post-treatment. It's just that there's so much of it that it was outside the scope of this presentation. But we have run filters, dual media filters, and we've run reaeration units and dual media filters downstream of anaerobic biological contactors, for example. and we've shown that we can consistently produce finished water that, for example, has that's back to saturated dissolved oxygen concentrations, that is has filter effluent turbidities that are less than 0.1 NTU, and which when the water is chlorinated with chlorine to hit 1 milligram per liter after 24 hours of hold, to hit a residual of 1 milligram per liter after 24 hours of holding time at a pH of 8, was water that consistently was in compliance with the 80-60 stage 2 disinfection byproduct rule standards for trihalomethanes and haloacetic acid.
Okay, great. Thank you, Nick. We've got one question about arsenic removal, but I'll just cover that in that I'll refer the person asking the question to our arsenic webinar that we presented prior. You can pull that up on the ASDWA site. I think it's just a little bit too long of a question to get into today because we only have a couple minutes left here. So this is another question for Nick. Was ORP used as a process control in either the aerobic or the anaerobic processes?
We did not. In the aerobic treatment study, in the aerobic process for ammonia removal, we used a Hock test for rapid feedback of how well we were removing ammonia, and the Hock test was always backed up with samples that we collected and sent to a lab for analysis by a method that allowed more QA and QC. And then on the anaerobic side, we used dissolved oxygen. Dissolved oxygen was very effective. And then we also used Hock assays for nitrate as to give us real-time feedback for how we were doing. And then what we found is we were finding really good correlations just between dissolved oxygen concentrations and nitrate removals. And once again, the Hock method was then backed up with with different analytical tests that we split out in the laboratory. And what we found is we found a good correlation between effluent dissolved oxygen concentrations and the efficiency of nitrate removal. So basically between dissolved oxygen concentrations with a dissolved oxygen electrode, and which gives real-time data, and and Hock tests for things like nitrate, we're able to do a good job.
Okay, thank you very much, Nick. We just have another question on whether or not ion exchange processes impact corrosion in the distribution system. Again, I think that's a little bit too long to answer on this webinar. We've done a couple corrosion talks in the past that are available on the ASDWA site. I think the short answer is with a resin like anion exchange resin, yes, you can change the corrosion indices of your water. So that would definitely be something you would want to look at if you had such a system. Okay, and then we have one more question for Dr. Boyer. When you did these studies, did you ever look at fluoride removal?
No, we haven't ever looked at fluoride removal. I think one could consider it. It's usually more effectively removed through sort of adsorption than a traditional sort of anion exchange process. But it's something that we could think about.
Okay, very good. And of course, we've in our small system workshop we had a activated alumina talk on fluoride removal, so we could have those resources available too. So that finishes off our questions. I really would like to thank our speakers, Nick Dugan and Dr. Boyer from Arizona State University. The fact that we pulled this off with Dr. Boyer in Phoenix, in Cincinnati, Nick Dugan in RTP, North Carolina, and our contractors in Boston, I think is just great stuff. Really, Buck Rogers kind of thing. So it's thanks so much for attending. Don't miss next month's webinar on September 27th, which is the title of that is Approaches to Technology Approval for Small Systems in Drinking Water. So thank you again so much for our webinar, and stay tuned for next month.